But at microwave frequency, inductance increase, as a result inductive reactance increase. You apply input to amplifier, but a major portion of input voltage that drop across the inductive reactance. As a result, the gain reduce. I will show you in the next slides. So, figure show triode, inductance exists at a plate terminal, inductance exists at a grid terminals, inductance exists at a cathode terminals. Now, see here, this one is a grid. When we apply a input signal to the grid, what happen? A part of input signal drop cross inductance, and it reach only a small portion of input signal to actual grid inside the vacuum tubes. Due to reduction in this voltage, the gain will automatically fall. So, at a microwave frequency, so this inductance increase. Due to this increase in inductance, most of the input voltage will lost across the inductance, and only small fraction of input reach to the terminal for amplifications. And even this inductance will with the parasitic capacitance or interelectrode capacitance can cause unwanted oscillations that will definitely create a noise or reduce the gain of the vacuum tubes at high frequencies. So, next is effect of transient time. So, now first of all, transient time. Transient time is a time taken by electron to travel from cathode to anode. At a low frequency, transient time are very small, but at a high frequency, transient time become very large. So, at that time, our in case of anode, in case of triode, when we are using triode as an amplifier, anode current will never follow the grid voltage. I will show you in the next slides. See here, electrons are moving from cathode to anode, and we are giving at a grid terminal, we are giving a signal for amplification purpose. When transient time is very large as compared to the very small as compared to a time period, that time it will not affect. But when transient time is large as compared to the time period of the signal, as case of microwave, what will happen? During positive half cycle, see here, during positive half cycles, the electron will emit from cathode, but as it reach in the center of the grid or cathode region space, so polarity change, polarity shift to the negative side, and electron will return back to the cathodes. So, as a result, the anode current will not follow the grid potentials. So, that is why this because of this transient time, because the transient time is very large, whereas the time period of the microwave signal is very short. So, that is why the number of electron from anode to node, they basically will not follow the change in grid potentials. So, due to this transient time effect, so microwave at microwave frequency, vacuum tube cannot be used. So, this will cause loading of a grid. The most of the voltage you are giving at a input terminal will lost across the grid, grid losses will increase. However, to minimize transient time effect, the distance between two electrode can be reduced, and or we can apply the high anode voltage. But as the distance between two electrode is reduced, the interelectrode capacitance will increase. So, this method is not applicable, or that means we can use another way is to reduce the electrode area, that means scaling of a vacuum tube. But still with this method we can't use our vacuum tubes for microwave frequency. So there are three factors that affect the performance of a vacuum tubes at microwave frequency. The first one was the interelectrode capacitance, second was the interelectrode inductance, and third was the transient type effects. So a special type of vacuum tube are used for amplification of microwave signal and for production of or generation of a microwave signals. So we are using a special type of tube for microwave amplification. They are Klystron tubes. Klystron tube is a vacuum tube that can operate either as a oscillator or a amplifier at a microwave frequency. The two basic configuration of Klystron tubes are multi-cavity Klystron, which is used as a low power microwave amplifier. Next is Reflex Klystron, which is used as a low power microwave oscillators. So multi-cavity Klystrons. So the multi-cavity Klystron, basically this tube use the same problem that occur at a vacuum tube. In case of vacuum tube, because of transient time fact, that tube fail to amplify the weak microwave signal. The same transient time effect are used in this multi-cavity Klystron to amplify the signals. Now this multi-cavity Klystron consists of a electron gun assembly here. This is a filament, and then cathode. As a current flow through a filament, the electron will be produced, and on the other hand this one is a collector that are maintained at a high positive potentials. So these electron will be collected. So there are two cavity, one is buncher cavity, another is a catcher cavity, and space between two is called a drift space. Now as the electron move from cathode to anodes, so we are giving here a microwave input. The weak signal that is to be amplified is given to the buncher cavity. What happen here? During positive half cycle, so electron will be accelerated, whereas during a negative half cycle, electron will be deaccelerated. What happened that time? So as the electron is moving, some electron velocity is more, that has accelerated by positive potential at input cavity, buncher cavity, whereas the electron that came here during a negative half cycle will be deaccelerated. So as a result, the electron will bunch together here. When that bunch of electron reach into and passes through a catcher cavity, and these electrons in bunch, they constitute a current. When that electron passes through this catcher cavity, it deliver a maximum energy or current pass to the catcher cavity, and catcher cavity, which is tuned to a microwave frequency, so it will oscillate. So amplified output will appear at a microwave a catcher cavity output terminal. So this way the weak input signal, microwave signal, we get a amplified microwave output. The principle is velocity modulation. Velocity modulation means the velocity with which the electron moving from cathode to anode are changed in according to the input potentials. During positive half cycle, what happened? Velocity of electron increase. What happened during negative half cycle? During negative half cycle, the velocity of electron decrease. So as a result, the electron, as the electron move from buncher cavity to catcher cavity, they bunch together. So as the bunch reach to the catcher cavity, it impart pulse. to catcher cavity. Catcher cavity is nothing but tuned circuit. So when we know when the tuned circuit is given a some energy pulse, it will oscillate. So you get here a amplified signal at a catcher cavity. So this way, this multi-cavity klystron amplify the weak microwave signal. So the application of this klystron tube are, it is used in ultra high frequency TV transmitter, in tropospace scatter transmitter. It is used in satellite communication ground stations. It is also used in radar transmitter. It is used as a power oscillator if used as a klystron oscillators. Next is a reflex klystron oscillators. So basically the reflex klystron oscillator is a oscillator that generate a microwave frequency. Now here basically there is only one cavity here. In multi-cavity klystron tube, that is two we have studied last, there are two cavity. One was buncher cavity, another was catcher cavity. Here we have only a single cavity here. So see what happened here, how it works. So now this is a cathode. When current will flow through a filament, it will emit electrons. And again here is a repeller. Now repeller is maintained at a negative potential. Again repeller is maintained at a negative potential, and this resonate cavity is maintained at a positive potential. As the electron emit from a cathode, they are accelerated by positive potentials of resonant cavity. So as the electron enter into this region with a high velocity, what happen? Because of some noise voltage here, during positive half cycle, the electron will accelerate. If the velocity is more, then it will enter deep into this region. Due to this negative potential, the electron will be reflected back to this cavity. Again the next electron, let it appear during a next positive half cycle, it will be accelerated and then return back. During a negative half cycle, the electron will be retarded. So that electron will return back with less time. It will not go deeper into these regions. So as electron move into this region, and when it reflect back, it will form a bunch, and these bunch of electron when passes through this resonate cavity, it impart current pulse to this cavity, and resonate cavity will oscillate at a microwave frequency to which it is tuned. So this way the reflex klystron, you get a high frequency signal, and that can be obtained from this loop, pickup loops. Now I have already told you from that basically it consists of a electron gun, a cavity with a pair of grid and repeller plate. Now here the repeller, instead of here are only one cavity, we are using only a single cavity that act as a buncher as well as a catcher grid. So main difference between two cavity reflex klystron amplifier or a reflex klystron is that the output cavity is omitted here. Only one cavity is used. It act as a buncher cavity during forward electrons and catcher cavity for when the electron are moving back from repeller to cavities. So how it works, I have already told you. When the electron emit during positive voltage, these electrons are accelerated. It go deep into the transition drift space region and return back, whereas the electron that appear during inactive potentials, they will immediately return back. On return, the electron beam once again enter the same grid which act as a buncher, and thereby same grid act simultaneously as a buncher for forward moving electron and catcher for returning beam. When the electron return back, so it impart energy to the buncher cavity. So, it start oscillating at a high frequency, that is microwave frequency. So, this way it will it oscillate at a high frequency, or high microwave frequency appear can be picked from the cavities. So, application of a reflex klystrons, they are used in a radar receiver system, local oscillator in microwave receivers, signal source in microwave generator of variable frequency, a portable microwave link, pump oscillator in a parametric amplifiers. So, last one is a tumbling wave tube amplifiers. So, tumbling tube is a high power amplifier that are more widely used because of its long life. So, its application is a RF amplifier, it is used as a radio frequency amplifier. In wideband communication link, tumbling wave tube are used due to its long life. It is used in communication satellites. Again, a high power, because of its high power, it is used in troposcatter links, and it is also used in airborne and shipborne pulse high power radar systems. Thank you very much.